So hello everyone, welcome to another particular lecture of the stereochemistry course, and this will be the final lecture of our basic stereochemistry course. So in this particular lecture, we are talking about the resolution of chiral compound, like how can we separate it, a particular enantiomer from the racemic mixtures. Okay, so first we are talking about resolution. As I already discussed, that resolution refers to the process of separating a racemic mixture into its individual enantiomers. So suppose a reaction mixture contain both R and S, and our topic of interest or our interest product is S enantiomer. So how can we extract S enantiomer from the particular mixture? And this actually discuss in the resolutions. Okay, now this particular process is not so easy since the both enantiomers have similar physical and chemical properties. So it will be very hard to extract one of the enantiomer particular with utter precision. However, there are some methods is there to resolute the particular racemic mixtures. Okay, so the first method is the mechanical separation, that is a crystallization. So the crystallization method suggests that sometime it has happened that either these two have same physical and chemical properties, but it has been observed that the both R and S conformer will show the different crystallization product, like their shape, their unit cell structure, and all the particular parameters are little bit of different. And from there, actually, we are doing mechanical separation. Like in tartaric acid, the R form and S form are shown different crystal structures. So someone can do a after crystallization, someone can do mechanical separation of the particular thing. But but the process is very time consuming and tedious. So there is another enzymatic separation was there. There is a biochemical separation that is observed in mainly in microbes or bacteria, where the both isomer can be produced, and by using the microbes having their own chiral environment, because they also body will produce some kind of chiral compound, and this particular chiral compound can interact with any of the particular enantiomer. And this is due to the fact I already discussed that enantiomers are physically or chemically same until and unless they are exposed to a chiral environment. Like in by applying microbes or bacteria, we are basically giving the natural chiral environment, and from there it is observed that some kind of bacteria will react only on the one of the enantiomer, and from there actually we are separating other enantiomer from the racemic mixture. Also, there are certain chemical separation is there, and we will discuss in brief the chemical separation. And the fourth is the selective adsorption or chromatography. There are certain chiral chromatography is there, especially HPLC. From there, actually, also we are determine the or separate the chiral compound. And the final is the complex formation. This is basically applying some kind of metal complex, and the metal complex has the audacity to react either one of the enantiomer, because the metal complex will also become chiral. If we add the chiral metal complex, then it also react only one of the enantiomer, either R or S, and from there, and it will be complex formation takes place, and it will be precipitate, and it will be out from the reaction mixture. And from there also we are doing the resolution. Okay, so let us talking about the chemical separation of enantiomer. This will be very important, and sometime it will come in the examination also. Not in the comparative exam, but for the MSc and all, the question can be asked frequently. Okay, so the racemic mixture was treated with some pure optically active compound, so that each enantiomer will prepare a diastereomeric pair. Now this will be very much important, since we know that enantiomers are practically inseparable in the chiral solvent. So what happened that we are adding a chiral pure optically active or pure chiral compound, so that these two will react and form a diastereomer. And since it is forming a diastereomer, we also know the about the uh, property of diastereomer that it will be no, it's not a similar physical and chemical property shown by the diastereomer. So since it will form a diastereomer, so now it will be easily separated by column chromatography and other kind of chromatography techniques. And after separating, we just simply remove the chiral part to get our particular compound. So from this flowchart, we can easily understand that here is the racemic compound is there. We are adding a optically pure isomer from outside, okay, in stoichiometric amount, obviously. So what happened that these two diastereomer has been formed. See here, plus minus and minus minus form is there. So these are nothing but a diastereomer. Now this particular diastereomer can be separated by fractional crystallization or distillation process like chromatography and all. So we are getting these two diastereomer, separated diastereomer. Okay. Now we just simply remove our initially added the optically pure isomer to generate our desired enantiomers from the racemic mixture itself. Let us understand by a simple example, like resolution of alcohol. So this is our alcohol which have the both enantiomer present in the particular molecule. So it will react with malic anhydride to form half esters. Okay, so till now it is not forming diastereomer. Now we are adding brucine here. Now, and the brucine is the negative brucine, that is the optically active compound. So now this particular brucine will attack with this particular OH and it will be bind there to form. Now these two become a diastereomer to each other. Okay, and then we are doing fractional crystallization, or we can do the chromatography to isolate these two compound. And these two compound, since they are now diastereomer, so the separation is very much easy. And now we are just simply adding the acid hydrolysis to cut down this particular compound as well as this particular bond. Okay, and so we are getting our desired alcohol or the desired optically active alcohol back. So here our point of interest is to generate the plus alcohol from this racemic mixture, and by this particular separation process we are easily getting this particular compound. Now we are talking about a very interesting thing, that is kinetic and dynamic kinetic resolution. So kinetic resolution is a process where a racemic mixture of enantiomer is separated based on the difference in reaction rate of enantiomer with a chiral reagent or catalyst. Now I again repeat the particular same thing, that enantiomers are showing different reactivity in achiral compounds. So it will be observed that certain racemic mixture or certain racemic mixture contain enantiomers are react differently with some external chiral compound or chiral reagent or catalyst. Sometimes it is observed that there is a X amount, X was adding in the racemic mixture. Okay, now sometime it will be observed that the R enantiomer present in the racemic mixture are mainly react with the X compound. It is our external chiral reagent or catalyst, and this is formed, but the S enantiomer won't interact. So from there also we are actually resolute, or we can separate our enantiomer from the racemic mixture. However, this particular resolution, kinetic resolution, has the maximum conversion of 50%, because we already know that racemic mixture contains 50% of R compound and 50% of S compound. So if the R compound is if the R compound is react with the X chiral reagent or catalyst, so only 50% of our desired compound can be extracted from the racemic mixture. Now there is another topic, that is a dynamic kinetic resolution. Dynamic kinetic resolution is an advanced method where the racemic mixture is subject to a condition that allow for the continuous interconversion between enantiomers during the resolution process. Okay, so here something that you should understand what actually written here. Like dynamic kinetic resolution is observed when the energy gap between the R enantiomer and S enantiomer is very less. Okay, so what happened that let us talking about this is our R enantiomer and this is our S enantiomer. Okay, and the particular energy gap is something like this. Now, if we add some kind of X catalysis here, which can react only with R to form Rx, and uh, it will not form any kind of product with S enantiomer. And if any kind of reaction won't happen in kinetic studies, we can say the activation energy of the particular reaction is very high, and that's why the particular reaction is not happen. So that means the if the Sx will form, it required very high activation energy. So obviously the reaction will go via this pathway. Since this particular is less, so this formation of this Rx will be favorable over Sx. Now, since the energy gap between R and S are very small here, so what happened in dynamic kinetic resolution? The S enantiomer are slowly interconvert to R enantiomer, and this R enantiomer will react with the X amount of product to generate the Rx compound. Okay, and this particular thing is due to this particular S enantiomer has transformed slowly toward R enantiomer, and R enantiomer are prone to react with the X, that is our chiral reagent or catalyst. So this from this particular method or dynamic kinetic resolution, we are getting our desired compound in 100% conversion. Like in dynamic kinetic resolution, we can say that we are actually disrupt the racemization, and here the reversal of racemization takes place, where one of the enantiomer has slowly changed to another enantiomer, and the mixture will slowly go to a optically pure mixture to form this particular component, and this is called the dynamic kinetic resolution. I hope it will be clear to you. Now we are talking about the chromatography separation. Here I also written the same statement again and again to emphasize that enantiomers have similar physical and chemical property until and unless they are exposed to a chiral environment. Now HPLC was used to determine the amount of enantiomer present in the mixture. Now what actually HPLC has interesting thing that normal column can't do. See, HPLC stands for the high performance liquid chromatography, and in any kind of chromatography, there will be two phases. One is the stationary phase and the mobile phase, and we will be discussed in brief in our analytical sections, analytical lectures. Okay. So here in HPLC, the stationary phase is chiral. Like the chirality can be observed by adding some kind of cellulose and amylose. They are the natural chiral compounds with silica, and the mobile phase is solvent. So what happened that when enantiomers are passed through the particular chiral environment, now depending upon the interaction, the R and S enantiomers are separate out each other, and in this particular chiral center, cut this part. So in this particular system, this is the HPLC system, and here is the UV chamber is there. So based on the UV chamber, we are getting this particular graph. This is graph of the eluent graph, like how much amount was, and if we calculate the area of the particular graph, so we get that what amount of enantiomers we are actually separating. Okay, so from HPLC we are also separate the particular enantiomers. Now, how to deter, like suppose you are generate a particular unknown chiral compound. Now you want to determine the absolute configuration of analytical method. Since you are actually prepare a chiral compound, this is unknown completely, and since you don't know that how to do rotate, how the particular compound has been oriented through space. So how can we determine analytically absolute configuration of your unknown compound? The most important and most useful method to determine the absolute configuration of unknown compound is to by a single crystal excited diffraction. So where you would just simply make the crystal of your optically active compound and do a single crystal XRD, and by using some kind of mm, data analysis pathway, you are getting the 3D orientation of your particular crystal, and from there we are determining the absolute configuration. Also, absolute configuration can be determined the NMR spectroscopy by using a chiral shift reagent. How? We are discussing about that. First, that the chiral compound that you are generated, the unknown one, is dissolved in the suitable solvent, and after that a chiral shift reagent. This is the chiral shift reagent. This is nothing but a chiral metal complex. Okay, is added to a solution, and this particular the shift reagent, the NMR has been known. Okay, so the NMR spectrum of the mixture is recorded. How now the NMR signal of the chiral center shift differently based on their spatial arrangement. Okay, and this, and from there we are actually previously know our first our the chiral compound that will be generated, that NMR spectra is recorded, and after adding the chiral shift reagent, the NMR spectra is again recorded. Now this both NMR spectra has a subtle difference in chemical shift, okay, are correlated with spatial arrangement of the subsequent, and then empirical rules were there certain, and some models is also there to use to assign the absolute configuration RNS. It is a little bit of tedious process, but from the NMR spectroscopy also we are determining the absolute configuration of an unknown chiral compound. Okay, so with this we have to end our basic stereochemistry part. In the next lecture itself, on the lecture 14 itself, we are talking about conformers and conformational analysis. So thank you for listening, and we'll meet on our next lecture with conformers. Thank you.